For this next unit, we'll start talking about different integration strategies that we can use to integrate functions that we couldn't before. So the first thing we look at is integration by parts. And the method for this is going to be described in this first paragraph. So the substitution rule, or U substitution, arises when we reverse the chain rule for derivatives. In this section, we'll employ a similar strategy and reverse the product rule for derivatives. So we'll go ahead and consider the product rule for derivatives. If we have two functions multiplied together, and we are going to be taking a derivative of that product, right, we do the derivative of the first times the second, plus the derivative of the second times the first. And so, just like with the substitution rule, we'll go ahead and see what happens if we try to integrate this. If we integrate the left side, the derivative and the integral will cancel. And so on the right side, we'll end up with an integral involving a sum here. And we can actually split this integral up over a sum. And we'll end up with two different integrals here. And so what we'll want to do then is we'll want to kind of take a look at our different functions here. And instead of describing u prime dx, we can say that that's actually just going to be du, right? It's going to be the derivative of u, just involving the chain rule where necessary. And likewise, v prime dx will be dv. It'll be the derivative, derivative of v involving the chain rule where necessary. And so we end up with two different integrals here in just v's and u's instead. And we'll go ahead and isolate u dv just because we have to pick one of them, right? And so we pick the alphabetically first one. So we'll go ahead and we'll subtract v du on both sides. And that's how we end up with integration by parts down here. And so looking back up here, we're looking at two integrals here and kind of examining the difference. This one we can easily do just because this is single function, essentially, and it's one that we have likely memorized, hopefully memorized. This one, however, is the product of two different functions. And there is definitely not a relationship that we can do U substitution with. So that's going to be our general strategy for finding when we're doing integration by parts or not. If there is a product of two functions and it's not a U substitution kind of fix, then we're going to have to use integration by parts. So we suppose that u and v are differentiable functions, and so we have the following. If we have the integral of u dv, we'll get uv minus the integral of v du. So we'll go ahead and evaluate one of these integrals. All right, so what we want to do is figure out which function should operate as u in our integral and which should function as dv. All right, so the idea is when we are going through our integration by parts, when we get to this point here, we're going to end up with v du. We're going to end up taking the derivative of u. So what we want to do is we want to pick the function, we've either got x or e to the x, whose derivative is simple. So if you take the derivative of e to the x, you get e to the x again. That's not any simpler. But if you take the derivative of x, you just get 1. And so it's going to be helpful to let u be x and let dv be e to the x dx. And so on the left side here, we've got du is going to be dx. On the right here, we have to integrate. So v will be equal to the integral of this guy, would just be e to the x. And so this integral that we start with can be written as u times v, that's x e to the x, minus the integral of v du. And so that'll give us x e to the x minus the derivative, or sorry, the integral of this guy rather is easy to figure out, right? We've seen it already. And so all that we have to do now is, since this is an indefinite integral, just add c to the end. All right. We can also do this with, say, x sine of x. Again, I'm seeing a product of two different functions, and I can't figure this out with a u substitution. All right, if I try to let u be inside the sign there, then the derivative is just 1, and that doesn't give me anything to do with the x. So we'll use the same strategy. U is x, because its derivative is simpler, and that leaves dv to be the rest of the integrand, sine of x dx. And so du will be dx, and v, we have to integrate that guy. We get negative cosine of x. All right, so our integral here will be equal to u times v, so negative x cosine of x, minus the integral v du, so negative cosine of x times dx. And so the negative on the inside and outside of those integrals will cancel. And so we get negative x cosine of x, and we integrate this guy, we get plus sine of x plus c. Always remember your plus c. So when should we use integration by parts? Loosely, when you see two distinct functions and substitution has not worked. When you see two distinct functions really multiplied together. All right, so what should we choose for u? As I said, we should choose a u whose derivative is simplest. How do we kind of order that? There are 5 types of functions we consider for u. In order of their desirability, we have logarithmic functions, right? So consider something like the natural log of x, right? That's a very difficult function to kind of deal with in an integral. But if we take its derivative, we get a rational function, and a rational function is going to be very valuable for us. Right? If we have a polynomial multiplied by our natural log, this will reduce all the powers. Right? That's a very valuable function for u. After that, inverse functions. So that's going to be like inverse trig functions, something like maybe inverse tangent. If we take inverse tangent in an integral, that's going to be virtually impossible for us to figure out. Except when we take the derivative of that, similar kind of idea, we suddenly get powers of x in a denominator, and it's going to make things much simpler than having that inverse tangent function there. After that, polynomial functions, right? That would be something like just x, or x squared plus 3x plus whatever. Because when we take those derivatives, it reduces all the powers. After that, exponential functions. The problem with exponential functions, this is kind of getting to the end of the list, where things don't work out so nice. Problem with exponential functions is that the derivative is often the same as the original function. So it doesn't get any more complicated, but it doesn't get any easier. And lastly, we have trig functions. Trig functions are the last resort for u. And that's because we'll not only not get any simpler, oftentimes we'll get more complex by maybe adding a negative in there. We'll switch back and forth between different functions. And so those will be the last resort. And so we have this mnemonic device, LIPET, logarithms, inverse, polynomial, exponential, trig. And those are the choices for u in order. All right, so for instance, if we're trying to evaluate this guy, we'll often choose, using LIPET, we'll use this guy here. That's that's not exponential, it's a polynomial as u. So du will be 2x dx. And the rest of our integrand will become our dv. Oops. The rest of our integrand becomes dv. And so we integrate that, we just get dvx. And so that means that our integral here will become x squared e to the x, that's our u times our v, minus v du in an integral. So v is e to the x, du is 2x dx. So I'll go ahead and shove that up here, put that guy back there. All right, and so we get kind of our first multiple step integration by parts here. I'm going to take this 2 out Right, so we have another integration by parts to do here. Right, so again, we have to choose u, and we have a polynomial here, x. So dv will be the rest of it. So du is dx, and v would just be e to the x. Right, so we get x squared e to the x minus 2 times, now we do our integration by parts, u times v, x e to the x, minus integral v du. So we've got our e to the x dx here. X squared e to the x minus 2 x e to the x minus e to the x. And so we just distribute that negative 2 there. So we got negative 2x e to the x plus 2 e to the x. And then lastly, this was, again, an indefinite integral, so we add c to the end. So we can end up nesting these different integration by parts. And when that kind of thing happens, what sometimes is helpful is there's a little table you can use. And you can actually, this is really helpful when there's a long list of these guys. Put in your u here, put your v in here, and just go ahead and take derivatives in this column, and then take some integrals in this column. Right? And so question might be what goes in this column over here. This is where you're going to put some pluses and minuses. And so what you'll do is you'll go ahead and really, there's an extra kind of plus here. You go by kind of diagonals here. We got this guy. Then we got this guy. Then we got this guy. And then we hit a 0 after that, so we're not going to write anymore. And you can see we've got x squared e to the x, that's this one, minus 2x e to the x, that's this one here, and then plus 2 e to the x, that's this guy here. So that's kind of a shortcut for doing multiple steps at once. It's not infallible, though. We'll go ahead and take a look at this next one here and see kind of the limits of that. All right, so we see here, we have kind of our two worst candidates, both in an integral. And so whenever you see an exponential and a trig function at the same time, you're pretty much guaranteed that this table is not going to work too well. It can get you to a certain extent, and we'll kind of take an examination of where it can lead us to, but it's not going to just spit out the answer. Right, the idea is our UV relationship is kind of at its worst. We're at the e and the t of LIPET, so we'll have to use e to the 2x for u, and then sine of x for v. So we go ahead and take some derivatives, and it's just going to be chain rule. We're just going to be spitting out more and more 2's. And I'll just do a few. This isn't ever going to go to 0, though, so we don't exactly know when to stop. And likewise, if we start taking some integrals here, it's going to be difficult to know when to stop here as well. And in fact, we've just made an entire loop. Right, we've ended up with what we started at. So we'll go ahead and see what that gets us. So we've got the integral of e to the 2x sine of x dx is going to be, well, we've got first little diagonal here, minus e to the 2x cosine of x, next diagonal here, plus 2 e to the 2x sine of x. And you can see we're just going to keep going and going and going, and it's not really going to be any help to us. So I would advise you not to use a table whenever you see this particular setup, when you see both an exponential and a trig function. This is definitely helpful for organizing the information and getting things done quickly when it comes to most other, I would say, most other integration by parts problems. But it does run into an issue, particularly with this combination of exponentials and trig functions at the same time. So we'll have to try something else. So we'll go ahead and do it the old-fashioned way. So we'll have to assign a u and a v, work through our formula, and we'll definitely have some repetition going on. Because at this point, we still don't even know, will this actually turn out well? So u equals e to the 2x, dv is going to be sine of x dx. So we've got du is 2 e to the 2x dx, and so v will be negative cosine of x. And I advise you, right, whenever we're doing cosine and sine, just do the derivative. Make sure you can go back. So from v to dv, just because I know that the negatives can sometimes be an issue. Should I have a negative? Should I not? All right, so we've got our integral here that we started with equals u times v minus the integral v du. And I have a negative here and a negative here. I'll just cancel those out. Right, and I'll go ahead and take out that 2 from my integral. And it's looking kind of suspiciously like we're going to have to do integration by parts again, right? It's almost the same, just a cosine instead of a sine. So we'll go ahead and do that again. And so we're going to have the same pick for u. So du will be the same. That was a terrible 2. Right, and v will be then sine of x dx. And so we'll go ahead and put this in now. Negative e to the 2x cosine of x plus 2 times whatever this integral turns into, right? U times v. So e to the 2x sine of x. Oops, that shouldn't have a dx on it, should it? There we go. Minus integral of v du. So 2e to the 2x sine of x dx. I'll go ahead and kind of clean this guy up. We'll probably take that 2 out and multiply this 2 in. So I take that 2 out, multiply by 2, we get minus 4 e to the 2x sine of x dx. So we actually got back to the same integral we started with, right? That's the integral over here. But wait a minute, we're trying to figure out the value of this. What if we think of it as y? Right, if we think of it as y, then on the other side of this equation here, we have just minus 4y. So why don't we add and get 5y? And that's going to be our sort of trick for this type of problem. So once we get back the original integral again, we can treat it as a variable, add to both sides, then divide. So e to the 2x over 5 cosine of x plus 2/5 e to the 2x sine of x. I'll go ahead and kind of swap the order. I like having the positive first. E to the 2x sine of x minus, let's call it 1/5 e to the 2x cosine of x, just for consistency's sake. And all that we need left here is plus c. That's our y value, which is our integral value. So specifically, when you see a combination of an exponential and a trig function, you're going to want to do it the old-fashioned way and kind of add on both sides. All right, x squared natural log of x. All right, so let's go ahead and try this with our table again. So remembering Lipit, right, first is logarithms. So we'll choose natural log of x as our u. And we'll go ahead and choose then x squared as v. So we'll take a few of our derivatives on this side, right? And as we go along here, let's see, we got 1 over x, that's x to the negative first, 2 over x to the third, and we'll go ahead and start with that and see what happens. On the other hand, here we have dv, so we'll go ahead and take some integrals. And we'll go ahead and just kind of see how this works here. So we start out with this guy here. So natural log of x times 1/3 x to the third. I'll go ahead and rearrange that. That was not the best way to do that. Right, minus 1 over 12 x to the third. Right, if we multiply those together. We need another one here. Let's see. We'll go ahead and take the integral. We got 1 over 60 x to the fifth. So it looks like we got a problem here, right? This is not really going to line up too well for us. Looks like we're kind of off by a second power each time. And so we'll go ahead and kind of strip all this stuff away then and see what happens if we go ahead and just do this the old-fashioned way. Right, so pretty much every semester that I decide to skip this whole table discussion, there's someone who asks me why, and that's pretty much the reason, is that the table can be helpful, but only in very specific circumstances. So I generally don't like to use it very much. So we'll go ahead and go to the old-fashioned way then. And so we have the same selection for u and v, and we'll go ahead and see what happens for us there. So we have du will be 1 over x dx, and v will be 1/3 x to the third. And so we'll go ahead and set up our equation here. So we've got uv, we had the same thing that we had before, minus integral v du. And so when we do that, we end up with just multiplying these guys together. That worked out a lot better. And so when we go ahead and integrate, then we end up with 1/3 times 1/3, that's 1/9 x to the third. And then we just add our plus c to the end. So the issue I find with the table is that there's probably some way to figure out what integral you end up with, and that's fine, but so far I haven't really seen that. And so the only times that I've ever seen the table really work in a convincing way is when your u eventually ends up as 0. So you're welcome to go ahead and use the table if you can figure out where to stop at the integral and such. That's okay. I'm just not going to rely on that. All right, so we're going to end up here with evaluating an inverse trig function in an integral. Right, and so that's definitely something that we wouldn't normally have been able to do to this point. But now using integration by parts and with a little creativity, we can kind of see what this actually should end up as. All right, so we know from Lipet that inverse trig functions are a good choice for u. All right, so dv, what's left? The only thing left is dx. And so that's what we're going to use. So v would just be x. And then du would be, remember, this is going to be 1 over root 1 minus x squared dx. All right, and then for inverse cosine, remember, it's just got a negative on it. All right, so our integral here will be u times v, so x inverse sine of x minus integral of v du. So we got x over root 1 minus x squared dx. And so if I'm looking at this function now, it's what have I really done for myself? Well, now if I look at this guy, it does look like a product of two functions, but if I look underneath inside this root, right, and I think of the derivative of this guy, I've got negative 2x. That's just a constant times this guy. This is prime now for u substitution, or the substitution method. It's not really going to use u because we have u already. In fact, we're going to probably have to call it w. So let w equal 1 minus x squared. And so dw, if I could draw a w, equals negative 2x dx. So negative 1/2 dw is going to be x dx. And so we've got now our substitution working. And so we have the x dx is now going to be negative 1/2 dw. And we have then 1 over root w. That's also going to be known as w to the negative 1/2. And so we'll go ahead and do the power rule here. So we have 1/2, increase the power by 1, and divide by that power. And so this will be our result then from this integral. And so that 1/2 and 2 will cancel. We'll go ahead and put our x back in. So you have w to the 1/2. It's 1 minus x squared under a square root. And the last thing we then need is plus c. So that's another kind of strategy that we'll see pretty typically is when we have what appears to be just one function in the integral symbol, we'll go ahead and make that our u, and then turn just the dx into our dv. All right, so we'll look at another strategy here, another modification. We have the integral of secant cubed of x. So this is definitely something that we wouldn't be able to do normally, right? And so what we'll want to do is we'll want to take a look at, well, this is a product of some different functions here. We've got maybe the product of secant of x times secant squared of x. And the idea here is we know lots about these two functions, right? For instance, we definitely know the integral of this guy. The integral of secant squared, that's going to be tangent. So this would be a good choice for dv. We should know also what the integral of secant is, but we're definitely more comfortable with the derivative. So we'll go ahead and look at it like that. So let u be the secant of x. dv will be secant squared of x dx. And so du will be secant of x tangent of x. And v will be, sorry, this should have a dx on it. V will be tangent of x. All right, so we'll go ahead and set up. So we've got secant of x, tangent of x, minus integral v du. So you've got secant of x tangent squared of x dx. All right, and that once again kind of leaves us in a bind here. All right, we don't necessarily know how to deal with this guy either. But we do have tangent squared. And the thing is, that doesn't really have any use in any context other than one in particular. Right, if we take our Pythagorean identity and we divide everything by cosine squared, and we get this relationship that the tangent squared of x equals the secant squared of x minus 1. And so that's what we'll want to use here. Right? We don't know anything about the we don't know anything about the integral of tangent squared, and the derivative of tangent squared is gross. So we'll go ahead and make that swap. So secant of x times secant squared of x minus 1. All right, so given that swap now, we'll go ahead and multiply in secant cubed of x plus secant of x dx. We split now this integral. This is addition, so we can split the integral over that. We do have this minus sign, so we'll actually turn that both into subtraction. And we see we have a copy of our original integral. Our original integral was secant cubed of x dx. So we'll go ahead and add to both sides. We get 2 times that integral. And we should know what the integral of secant of x dx is. Right? If you do not remember from Calc 1, you should have looked at this. But this was kind of a trick integral. You actually have to multiply by a fraction here. And so you get secant squared of x plus secant of x tangent of x over tangent of x plus the secant of x dx. Right, and so we have a u substitution here. We have the original function and its derivative. So this is going to end up being the natural log of the absolute value of the tangent of x plus the secant of x plus c. And so we'll go ahead and make that swap here. Tangent of x plus secant of x. And then we will divide by 2. Sorry, I think that actually should still be negative, shouldn't it? So yeah, that should have been negative there. And when I distribute that negative, this should make this positive. This should be positive. That looks better. All right, so we'll go ahead and divide by 2. So you get 1/2 secant of x tangent of x plus 1/2 natural log absolute value of tangent of x plus secant of x plus c. And if we want, we can pretty this up just a little tiny bit here. Arguably not very pretty, but if we take this 1/2 and make it the power of our argument there, this will become square root of the absolute value of tangent of x plus secant of x. I think I like it a little better, but you could argue either way. All right, so that's another option. When we have something to a power, when we have a function raised to a particular power, we have the option of kind of splitting it up into 2 different pieces and making one piece our u, making the other piece our dv. So the last sort of concept we'll touch on with this particular section is how do we take our integration by parts and work it for definite integrals. there's two options. So first, you can just find the antiderivative and then evaluate. If you do that, you're going to have to be careful. You don't want to set your antiderivative equal to a definite integral. You're going to have to make a separate indefinite integral. Alternately, the limits of integration can be incorporated directly into the integration by parts process. So both of these might seem kind of vague. We'll go ahead and take a look at both. So first off, just definition. If we have, this is kind of the second option. If we have a definite integral for integration by parts, then again we have uv minus integral v du, but we have the evaluation happening at the same time. So we have the valuation of the first kind of term, and then we have a definite integral on the second. So we'll go ahead and see how both methods work in practice here. So first off, we'll do kind of the definition up here, which is the second option here. So we'll go ahead and do that. Integral from 1 to 2 of natural log of x dx. All right, and we have just one function, it appears, right? And so what will happen is we'll go ahead and use that dx as our other function. So we'll let u be, remember LIPET, we have logarithm first, natural log of x. So du is 1 over x dx. That leaves dv to be dx, and so v is x. And so when we put this together, we have u times v, but we're going to evaluate from 1 to 2, and then we subtract the definite integral, and then we have v du. And so we have x natural log of x from 1 to 2 minus integral of 1 dx. Right, so we get x natural log of x minus this integral becomes x as well. And so we're going to evaluate this whole thing from 1 to 2. And so when we do that, we get 2 natural log of 2 minus 2 minus 1 natural log of 1 minus 1. Natural log of 1 is 0. So we get 2 natural log of 2 minus 2 plus 1. We can make this 2 on the outside the power on the inside, so natural log of 4 minus 1. And so it looks like the notation is way different, but in reality our process is basically the same. It's just at the end we are adding this evaluation step. So that's one of the options that we have for evaluating a definite integral using integration by parts. The other option we have is really just to remove the definite part of the integral and just say, what is the antiderivative we're looking for here? Right, and so u would be natural log of x, dv is dx. It follows the same process as before, and so v would be x. And we'll go ahead and just pretend that this is an indefinite integral problem. So u, v, minus integral v du. And so we get x natural log of x minus this integral here. We just get dx. And so we get x natural log of x minus x plus c. But our problem tells us to find the definite integral. So what we then do is we say, okay, I want to take the definite integral, which means I need to evaluate an antiderivative at these 2 points. So I'll go ahead and take the antiderivative that I've found and evaluate from 1 to 2. And so we end up with what we had before. And so the same thing happens then from basically here on out. So we get natural log of 4, this guy becomes 0, minus 2 plus 1, natural log of 4 minus 1. And so there's not a whole lot of difference between them, just practically speaking. But there is a lot of difference just making sure that we're being mathematically rigorous here. So either way is going to be okay. I'm not going to ask you to do a specific way versus another way. So it's just whichever one you're comfortable with. All right, so that's going to end the section on integration by parts.